Hello everyone, good evening, and my name is Ambar Prajapati, and today I will be presenting my paper, Reliable Multicast of Dynamic Content Streams from AMQP to NORM Protocol-based systems. What we are trying to achieve here is to build efficient messaging pipelines to thousands of simultaneous recipients over high-performance networks. So we are talking about a large group of simultaneous recipients, and we are talking about high-speed networks. And on the other side, we are also talking about the dynamic content streams. So the objective here is that how we can stream the contents which are dynamically produced at a very high rate to thousands or a very large number of simultaneous recipients. So this is what is messaging to multicast. So here I'm exploring the messaging protocol AMQP, which is a platform agnostic, vendor neutral, interoperable messaging protocol across the heterogeneous networks. It uses building blocks like type system and layers like transport, messaging, transaction, and security. Uh, it contains immutable bare message consisting of standard application properties and application data, which is the body of the message. And its connection features involves a model with a connection, authentication, session, and link to publish consume messages, and it allows connection multiplexing. That means multiple conversations where multiple flows could be could happen at the same time. It offers connection recovery and data delivery guarantee. That means mechanism to resume message transfers during service failover or intermittent connectivity. It does it by a message caching, stored forward mechanism, and acknowledgement for delivery guarantee. On the other side, for multicast operation, we are using NORM, uh, which is a NACK-based reliable multicast protocol. Its main functionality is NACK, that is Negative Acknowledgement based reliable data transport in IP multicast groups for simultaneous reception. Its building blocks constitute of transmission strategies for multicast sending of packets, repair and round trip timing for NACK-based reliable multicast, and the messages are actually the data consisting in the UDP datagram field, which could be a static data, a file, or non-finite ongoing stream. It has the features like the connection for it has the features like connection multicast one to many, or connection oriented, which is point to point, and it allows asymmetric connectivity. So for connection recovery and data delivery guarantee, it uses pre-designated port numbers and addresses to quickly resume the session after any network outage. It maintains the state, does buffering, and it has forward error correction and negative acknowledgements to ensure full data propagation. So the quick facts that we can check side by side for both these protocols, that one belongs to application layer protocol AMQP in the OSI model layer, whereas NORM belongs to network layer protocol group. The applicable RFCs for AMQP are OSS standard ISO IEC 19464, and NORM has the RFCs stable RFCs standard track 5740 and 5401. The major open source implementations for AMQP are like RabbitMQ, Apache MQ, Red Hat AMQP, OpenStack, etc. And for NORM, like NRL NORM repository. Major implementation programming languages are C, C++, C Sharp, Python for AMQP, whereas for NORM it is C, C++. Some of the noteworthy users of AMQP are NASA, Dashbosh, IBM, Red Hat, VMware, JP Morgan, etc. And on NORM side, we have NASA with its sample application, transport of spacecraft telemetry in ground networks. Next, we'll highlight where this simultaneous reception can happen. We have to have a multicast group, IP multicast group, that uses a common class D IP and port numbers among the members. So sender, router, and the receiver, basically they all should be using norm. Sender and receiver must be using the same class D IP and the port number so as to form a group. uh, RabbitMQ, NRL, and norm DLL, I mean, the kind of integration mechanism we are using here is like on the left hand side we can see RabbitMQ symbol. That means there is a RabbitMQ implementation involved. I'm using here the C# version, and on the right hand side there is a NRL norm API which is in C++. So we need a wrapper for which we utilize the interop namespace from Microsoft. So that calls out the routines in C++ and is able to penetrate the NRL API and execute its functions from C#. Okay, so this is how they bind together. And this is the process flow I'm using. So on left hand side we have at the bottom message producer, RabbitMQ message producer, which continuously streams messages, and we have the wrapper which passes it or invokes the API of norm sender, and which via the router it sends those messages simultaneously to a number of recipients. This is the mechanism or the process flow that happens. So we performed this operation, and the evaluation results can be seen. Um, we performed the UDP multicast stream analysis. So total 3004 packets were sent, out of which norm receivers received 2933, and the speed was 632.4 for norm sender and 622.25 for norm receiver. We talk about network throughput, so which is like packets per second. So average packets per second were 177.8 for norm sender, whereas for norm receiver they were 163.4. Uh, and the bandwidth, we have the maximum bandwidth available as 1189K on sender side and 1513K on the receiver side, out of which 445 and 437K only was used at the sender and receiver respectively. The packet delivery ratio, like the total packets that were transmitted and received. So ratio of received versus transmitted packets is the percentage of that is PDR percentage. So here those values are 3104 divided by 3159. So we get a PDR of 98.26%. One more interesting thing is how they perform the congestion control. So here I'm showing the arrows with the flows, how the data was flowing. So the norm sender at this particular designated IP was sending the data packets. The total count was 3004, and there were congestion control packets 4 via the multicast IP shared between sender and receiver. So norm receiver also sent two acknowledgement packets to inform the sender to perform some kind of congestion control. So that's the norm mechanism of controlling the network flow or reducing the rate in some way. Conclusion is that what we saw, that messages could flow from RabbitMQ to a norm sender to several norm recipients. So it is, and we saw the good network throughput, packet delivery ratio, and link utilization. And we also saw that norm nodes were performing automatic congestion control during the multicast burst. So it seems that AMQP based messaging with norm based reliable multicast is good to try and test in scenarios where we do need messaging combined with multicast. But we might need some architectural considerations fitting the appropriate scenarios or the implementation that we want to use. Future work is basically probing backward communication from norm sender to the producer, AMQP message producer, to relay message acknowledgement guarantees, because this work demonstrated the forward communication. So there is some future work that could be performed to show the backward communication. On the second item I have here is deducing appropriate considerations for building specific network architectures to integrate AMQP norm applications. And third is performing volume or network load test to verify integrated AMQP norm limits for message multicasting. And from the protocol point of view, a precise non-ambiguous definition of interoperability between AMQP norm system is desired. And if we take the industry experience considered, probably we'll be able to come up with a properly clear guidelines how we can integrate AMQP norm in a more standardized way. So thank you, and hope you liked this paper, and it will be useful in the upcoming days. Thank you. Bye bye.